Hello and welcome to this video covering the creation of basic math models for the evaluation and selection of design concepts. My name is Jim Heisey. I'm a senior lecturer with the Department of Mechanical Engineering, and I'm recording this video lecture for mechanical engineering design classes such as ME 270, ME 415, ME 466. If we look at system modeling, it is critical in engineering design that the concept generated is the best combination of systems that will fully meet the critical performance criteria as defined by the customer or customers. To accomplish this, it is very important to be able to translate qualitative criteria into quantitative performance targets. By doing this, the engineering team can then model their various concepts in order to evaluate them to determine which concept will best meet the performance targets. Through modeling of the systems, the engineering team can determine which design parameters are critical and what values they must be for the design to achieve the desired success. If we look at the system modeling process, it can be accomplished in many ways using many tools. The critical requirement here is to capture all the performance measures that must be met and to determine the interactions between design parameters and the performance quality. In this course, we have focused on design for Six Sigma process, otherwise known as DFSS, to establish a discipline to enable the engineering team to increase their chances for success. The process we will outline here in this video lecture will be defined by a six-step process as shown here. Key points of each step are highlighted in this slide. The process relies heavily first on the team establishing a function structure for the design so it can develop a system block diagram for the design and to determine all the required actions of the system. Next, the team will identify all quantitative inputs and outputs as defined by the block diagram, and will do so for each subsystem that makes up the system as a whole. Once all of these inputs and outputs have been determined, looking at units and balancing units from inputs to outputs, the team can develop conversion equations for each components box. Here, oftentimes, the use of free body diagrams will be needed, and that is called an abstraction process. The next few slides will go over what that is. The fourth step in the system modeling process is going to be to perform the analysis once we have all of the conversion equations determined for our systems or subsystems. And then from this analysis, get the performance results allow us to select the appropriate components based on the desired performance results. This analysis will also allow us to select what should the values of the design parameters be that will provide for us the optimal performance of the system. Now, it's quite common in this process to have to iterate through steps 4 and 5 to refine the abstraction analysis and to get the optimized design. The abstraction process is something that you must do as an engineer. We can define abstraction as, in its main sense, it is a conceptual process by which general rules and concepts are derived from the usage and classification of specific examples. This is the most critical process for the engineer to get right because mistakes made here will have a lasting impact on the success of your design. You'll be required to define the system by its features, which must be present in order to fulfill the required actions. This is often done by creating simple geometric models of the system. Free body diagrams are often the most common method employed for this to extract equations of force and motion. Once these equations have been created, then analysis and optimization of the design can begin. The examples shown here in this slide are three classic engineering situations that occur commonly in putting models together. The first example in the upper left shows a block sitting on an inclined plane. And in this case, we're defining normal force, the weight of the block, and friction. The illustration in the upper right would show a bar being grasped by somebody and being pulled. So we have two reaction forces, and that would cause stretching of the center between the two grasping points. The third one is a simple kinematic link showing a crank and slider and giving denoted labels for nodes and, and linkages and angular positions. These illustrations are classic because they would help to define what sort of parameters or variables would have to be defined in coming up with a system model. Another example of the extraction process, here we have a gantry or crane in a shipyard used for the lifting of cargo or lifting of components used in shipbuilding. In order to abstract a model out of this picture, we would first need to take the system and identify its subcomponents or subsystems. In this case, we can take this gantry and break it up into the boom and the base. From there, we would want to create some sort of equilibrium looking at forces. In this case, this gantry, as you can see, has a cable for doing the lifting, but in order to balance it about its pivot point, it has to have a counterweight, which is shown by the black arrow on the right. So in the end, our free body diagram, we make a simple representation of the truss work, showing the forces due to the weight being lifted and the counterbalance acting on the back of the crane. From there, we can understand that there is a vertical force reaction that goes along with this, along with a potential for a bending moment about the pivot point. Last part of the model, we'll look at the base, and the concept would be it's a simple U structure upside down. So from there, we need to, from a free body diagram, understand some basic dimensions and forces involved here in supporting the crane, and what the reaction forces will be at the interface between the base component and the boom component. Once these are defined, forces and moments, reaction points, we can now begin to generate the equations of force to do the analysis on this system. Abstraction of linkages are quite common. Again, here the illustration on the right shows a classic crank and slider, but we can also utilize kinematic analysis to define human postures and human motions. The illustration on the left shows a leg in its classic motion as it would be for either walking, climbing up the steps, or pedaling a bike. Key thing about kinematic analysis is we're usually looking at positions and velocities, and oftentimes to acceleration and force. These are all critical when determining forces and stresses and powers that could be generated by a system. So our concept generation steps, what we're looking at here and doing the math modeling is first we want to, using the function structure design approach, define or break our system down into sub-functions, define cross-component relationships. From there, develop the required engineering specifications. From this, we can generate the ideas that would accomplish these sub-functions. From there, then we can pick and choose, that is through analysis, what are the best ideas that would create the desired design concepts. And then lastly, evaluate our design concepts and choose the best design. So if we look at our tools that we typically use for breaking the design down into sub-functions, we're going to start with function trees and identify the systems and subsystems in our design that we're wanting to put together. From there, we'll generate ideas using a morphological chart or morph chart, we'll call it that for short. And this will help us to identify various different types of sub-functions we can put together and their interrelationships. From there, we're going to use functional analysis, block diagrams, and create math models to analyze our system. And then lastly, put that information into a decision matrix to evaluate the concepts to choose our one best design to move forward with. So the flow down of the process, put together requirements, that is looking at the qualitative requests that the customers made, turn that into quantitative parameters that we can design to, engineering specifications. From there, we want to take and define those specifications into actions and do that through creating a function tree, which then would help us to develop concepts utilizing morphological charts. From there, once we have concepts put together, use abstraction and the functional analysis block diagram to create models of our systems, create the analysis, which would then give us information to feed into decision matrix, which would allow us then to pick the best overall design. So again, we're going to emphasize modeling of systems here, allowing us to get the information into decision matrix. So to get started, first we got to look at the complete system definition. So define the physical requirements, do any reverse engineering if needed by looking at similar systems, or do exploratory testing if needed. Those last two steps shown here are often referred to as benchmarking of the design. From there, we can model the system by using function block diagrams, looking at the function flow through the system, develop the equations of force and motion, understand kinematic constraints, and pull in material specifications as well in order to model the system and understand what its performance is going to be based on measurable targets that we identify through putting together the system definition. Key thing what we're looking at here is we're wanting to understand when we're dealing with a system and its subsystems, we're looking at inputs. Inputs would be variables that would feed into some action that would wind up giving us an output or a performance result. These are often impacted by controls within a system, which we would refer to as design parameters. More often than not, when dealing with a system, we're looking at either three key areas, that is converting energy or work or power, or taking materials, converting them from solids into liquids or gases or plasma, or processing signals, whether it be tactile, audio, visual, or olfactory. That is the sense of smell. So let's look at some basic examples of putting a math model together for an engineering system. Let's say we're creating a hand crank generator to charge a battery for either a cell phone or a lighting system or a laptop computer. If we're talking about a human powered system, then we have to have some sort of way of putting input, and that input system is going to utilize force, distance, and velocity. That force could come from a hand, could come from a foot, but in order to create work, we have to have force going at a distance. In order to create power, that has to have velocity behind it. That input system, if we're going to turn a generator, classic generator is going to require rotational movement, and it's generate power, we have to have some sort of torque that is going to have to be present along with the rotational speed to get power. From there, the generator is going to take this mechanical power and convert that into a voltage pressure, which is going to result in a current flow in the wiring, which would be amps, and that would deliver power into the battery to be charged. So we've got our basic relationships here. If we take a look at classic generator design, we can understand that voltage is going to be proportional to rotational speed, and current is going to be proportional to torque out of the generator. If we understand these relationships, then we can pull together a mathematical model. One of the steps that we've done in the past with modeling systems is we've put together some testing of a generator in order to understand what was its relationship between the voltage it would put out versus rotational speed. And hence, given some defined load, in this case we had used a 23 ohm power resistor, what would be the resulting torque requirements of the generator, and then hence its power output and its efficiency. That testing resulted in the chart you see here, which then using curve fitting we were able to determine some basic equations in relation to torque requirement as a function of rotational speed, and the power output as a function of that rotational speed. Also the voltage generated with respect to rotational speed, and the efficiency of the generator as well, looking at the power out versus the power in. So with that, we have enough information that we can put together a math model. So we take a look at a functional analysis, a function block diagram. We can see our first conversion is to take force and velocity and distance, convert that into torque and rotational speed. We created some classic equations here. Torque would be for instance here could be a crank arm. with force applied at the end of it, which would create a rotational torque. And a rotational speed would be taking the velocity of the hand motion and turning that in, or dividing that by the radius of the crank in order to get our rotational speed and RPM. Also, we take a look at torque. Torque on the system is going to be whatever the input torque is divided by the ratio, and the rotational speed is going to be the rotational speed times the ratio. That is speeding up to the motor. So now then we get to the generator itself. Now we see the generator equations coming into play here, and we've got them listed. You'll notice here though that as we're doing this, that what we have boxes here for mathematical models, as indicated by my cursor here going around the box. And we can see that each system block has a modeling box that goes with it, and we've identified our inputs, our control parameters, and our outputs within each subsystem box for analysis. You'll notice that the bottom box with the generator has no parameters there because these relationships are fixed by the characteristic of the generator through the testing that we did, so those equations are set and highly dependent on what is going on with the input system. So we can either use a top-down approach and solve looking at inputs and what that would require out of the system for outputs, or we can do a bottom-up approach, look at our outputs, and then determine what sort of inputs would have to be there in order to get those performance results. These are two classic methods of doing engineering modeling. So we look at top-down versus bottom-up approach. In a top-down, we would define first maybe the velocity and the distance to which we're stroking on the input system. From there, determine rotational speed, then based on the information that we have from the generator, determine the torque that would be present at that rotational speed given our voltage that we would get out of it, and the current that would be present due to the impedance of the load that the generator is charging to. From there we can back solve through our system and get the force required. In a bottom-up approach, we might go ahead and determine first what our voltage target is for our charging, then using the generator equations figure out what our rotational speed is, and then from there back solve through to determine what our cranking velocity is going to have to be and our cranking forces would be. More often than not, if you're trying to determine the best design, you'll probably wind up using the bottom-up approach. So again, we take a look. We've got this hand crank generator model pulled together here. This would be an example like what we would do in Excel. You can see we got our input parameters, the force on the crank and the velocity on the crank. Those are denoted here in the Excel block and in the green as indicated by the circle there. We've got our design parameters, the crank arm radius or distance, and also the gearbox ratio that the crank arm is attached to, and those are denoted in the Excel box over here with these input values. Finally, we have our outputs, which are going to be represented here. And those are going to be defined by the equations that we have. So if we look at what we're doing here, we have our parameter force, which is shown there, our velocity, which is here on the rotational speed, which is represented there. We have our crank radius, which is represented here and there on the model, the ratio, which is going to show up here for rotational speed as well as torque. That's going to be represented there. And then finally, if we take a look at our output torque and omega, those are going to be showing up here and here on our box. Now you'll notice that we have the torque on the system is going to be defined by the torque of the input divided by the ratio. In this case, that's because the box is speeding up. Also, the rotational speed is going to be whatever the input of the system is times the ratio. And here again, because we're speeding up to run the generator at a higher speed, we're going to see that we're going to get a reduction in torque based on the hand crank to the motor and we're going to get an increase in speed. So looking at our modeling system, we have our equations here for the generator, and those will give us our outputs here in the Excel model if we insert these equations into these cells in the Excel model. These models can also be done using um, Ease or MATLAB or MathCAD. Any of these analysis softwares work well, or they can be done simply with an engineering problem paper and writing out the equations longhand and solving them on a calculator. Important thing is document your analysis so others can understand how you came up with the results that you have. So if we take a look now at the top-down approach, we have these values here, and they're going to get their inputs from the previous box going to go. So we have outputs becoming inputs, which is also represented here by these color boxes, as you see on the functional analysis diagram. And that allows you to track what you're doing with your system model. If we take a look at the bottom-up approach, we'd say, okay, we want to get this sort of voltage, so we're going to have to back solve with equations to understand what our required torque and omega is going to be at the input of the generator, and then from there, what does that require from our system from a standpoint of force and velocity at the hand crank using the bottom-up approach. So from there, once we understand that, we have our equations that we can back solve to get us those values. Oftentimes, in doing modeling like this, you're going to use a program called GoalSeek. GoalSeek is an analysis tool in Excel that's very useful for what-if scenarios. It's very easy to use, and it's a significant time saver when having to do optimization on your design. How do you use GoalSeek? Well, if we look at Excel, on the menu bar, you'll find an area called What If Analysis. If you select on that, then it will pull up a menu bar, and in that menu bar, you will see GoalSeek. Select on GoalSeek, and you will get a window that has 3 cells in it that you need to select for. So the first one is you're going to select in the dialog box the cell that you're wanting to set, that is to get a value for. So we might select, in this case, we're going to have a goal that we want to have a certain wattage output, so we want to hit a particular value. In this case, we put in that we'd like it to be at 30 watts. But now we have to determine what cell are we going to change in order to get that based on our equations. And in this case, we're probably going to look at input force to get that wattage, or input speed. So we'll do this by changing that cell, M, in this case it's M10, and then hit OK to do our analysis. In the end result, we'll find that to get 30 watts, we're going to have a force of over 97 newtons. That's going to be somewhere in the realm of about 25 pounds of force, or 22 pounds of force, which is pretty heavy for generating that. So to reduce that force, we might wind up using a longer crank arm. In this analysis model here, though it's cut off, the crank arm radius is 0.2 millimeters, or in this case 20 centimeters. We could increase that crank arm slightly longer to 30 centimeters, and it would reduce the force by about 50%. So again, we got an output of 30 watts, requiring our force of 97.7 newtons. We can break modeling analysis up into 2 areas, what I would call basic and advanced. In basic modeling, we're just wanting to understand the relationship between the inputs and the outputs, probably going to ignore losses, and in most cases we're trying to do just a very rough estimate so that we can make some basic comparisons on our concepts to find the best one we're going to move forward with. As we get further on in the design, then we'll look at doing advanced modeling. We'll get more specific. We'll take a look at losses and understand efficiency in the system. We'll also understand stresses and look for failure points. Often too, we'll do independent models of specific components, in order to optimize the components themselves. And in most cases, we're going to have a much tighter accuracy in our model because we're wanting to make sure that we fully understand the values that we have to make the best performing, the least cost system that we can put together as an engineer. The reason we do this analysis is oftentimes when we're doing concepts, we're creating something that's never been created before. We can take two approaches to this. As engineers, we can do models using analysis, using mathematics, and come up with values such that it drives our design so that when we finally do sit down at the CAD terminal and work on our design, we'll have a good idea of what our system's supposed to be. Or we can do trial and error. We can sit down at the CAD terminal first, come up with the designs, build it, test it, see how it performs, and then make adjustments as necessary until we come up with a working design. Practice nowadays with engineering is to do the former rather than the latter, because it has been proven that this system of doing analysis first followed by design and fabrication can oftentimes lead to getting a full functional design on the first pass and not have to go through design iterations 2 or 3 times in order to come up with a workable system. Doing the analysis here and getting the numbers, oftentimes when we take a look at a QFD, what we're trying to do is understand our performance targets and identify functions, and those are indicated here on the QFD. You can see that performance functions are out of section 2 out of the QFD. The functions we're going to determine come out of section 6, and what we're trying to do through analysis is understand what are the function outputs, that is getting the data filled out in section 8 of the QFD, such that we can then make assessments as to how well does the system perform in room 5 of the house of quality. And by doing that can get a much better or accurate assessment of our system and ensure ourselves of picking the right system to move forward with in development and the design. So again, we're identifying performance targets to identify functions which go into the QFD and allow us to model to get function outputs. From there, put that information into our decision matrix. So after modeling performance functions and subfunctions, we can also assign cost or values to these performance parameters and compare the system, subsystems, components among the designs to ask ourselves, how well do they go about fulfilling our system requirements? Are they cost effective? Also, by doing this analysis, it can help us to understand ahead of time, do we have the fewest parts possible? Is it the lowest cost? We can also look at our design, ask ourselves, is it easy to manufacture? Is it the most robust design possible? This can all be determined through good engineering analysis and will save us significant time. So again, you'll use analysis to help you to fill out your QFD or decision matrix so you can benchmark and come up with the best concept that you can put together, and also allow you to compare your concepts to competition that may be out there in the market. Competition, you usually have data available, but you won't have data readily available for your concepts, so you have to do the modeling in order to get the results. In the end, your analysis will save you time when you sit down with CAD and design your product, because you will have an idea through your analysis exactly what your parameters should be, such as the length of your crank or the size of a gear or the ratio that has to be in a gearbox. You'll know ahead of time what it has to be, and it'll save you valuable time in getting your system engineered. So what tools will we use for engineering analysis? Well, looking at from the simple to complex, you could use engineering problem paper, pencil, eraser, and a calculator. Usually you would want to do this in some sort of logbook. That is a classic method. This has been used by a lot of engineers through the years. As simple as that sounds, it's actually a very effective way to chronicle what is being done in the design, and in a court of law, an engineer's logbook is usually the final word on a design. Also, you can use Microsoft Excel. We have that available in the Demandver toolbox, or you can use Ease, MathCAD, or MATLAB software for doing your models. You can also model systems in any of our typical CAD packages we have available: Autodesk Inventor, SolidWorks, or Pro Engineer. I do want to caution here, though, that when using CAD packages for doing modeling of systems, you want to make sure that your constraint systems are correct. Otherwise, you could wind up with incorrect results. Same is true for using ANSYS or ADAMS. ANSYS would be typically used for finite element analysis, stress analysis. ADAMS would be used for motion analysis. Here again, constraining and meshing are critical for those systems to give you accurate results. So often when using ANSYS or ADAMS, it is highly recommended that you back up your analysis with some hand calculations for some of the basic areas so that you know that the results that you're getting out of your analysis software is correct. So expectations on modeling. We want you to use whatever method you're most comfortable with, but make sure to double check the most critical aspects of your design that you've got your analysis right. Model the most critical aspects of your design. You don't have to model everything to make a decision, so understand which performance criteria are most important. Model that first. It'll probably save you a lot of time if you can cut down to the most critical factors, the 2 or 3 elements that have to be met, rather than modeling 10 or more items in your system. Hint here, take a look at what aspects of your design are most at risk for you. Start with those first. If it's a safety issue, look at that. If it's a critical performance issue, make sure you cover that as well. That concludes the lecture for math modeling. If you have any further questions, be sure to see your instructor, as they will probably have excellent advice to give you. Again, my name is Jim Heise, and if you have any questions on this lecture, you can feel free to contact me at my email address, jheise, Jheise, @iastate.edu. Thank you.